Hello everyone. So in the last class we had discussed about DL and L configuration, how to find out the number of stereoisomers for a compound. And now today we'll be talking about few small topics which are left, like racemic mixture, polarimeter calculations, and alternate axis of symmetry. And after this we'll be done with optical isomerism. So let's see what we are starting with. We are starting with racemic mixture. So now all of us know that your compound, an optically active compound, can be represented by D and L configuration, which is called as the relative configuration, R and S configuration, which is called as absolute configuration, and plus and minus. I mean, there are multiple ways you can represent it. Okay, so basically to tell their optical activity, you can use various methods to represent a optically active molecule. So what is racemic mixture? Racemic mixture is when the two enantiomers of a compound which is optically active, two enantiomers when we take in the equal moles or equal number, or you can say in the 50-50 proportion, and mix them together, so that mixture is called as racemic mixture. For example, if I have a compound, I have taken 50% of R of it and 50% of S isomer of it. When I'll mix them together and make a compound, that will be called as racemic mixture, and R has a particular optical activity which is opposite to the S optical activity. Basically, the angle will remain the same, but if you talk about the directions will be completely opposite. If R is dextrorotatory, assume if R is dextrorotatory, your S is gonna be levorotatory with exactly same angle. So when we will mix them together in the equal moles, we will pass a light through that solution, what will happen? Will it divert, or will it show you any kind of, when we'll pass a plain polarized light, will you see any deviation on its path or any shifting towards right or left? No. Why not? Because now the mixture what I have is R and S both. So R 50% of R will move it to one direction and 50% of S will move it to the another direction. Hence the compensation will happen. So basically whatever the movement has to happen, that will get compensated, that will get cancelled by each other, and hence when the light will come out, the plain polarized light will come out from that solution, that will be unaffected, or you can say it will not show, the solution will not show the optical activity, and there will be no change in the angle of the plain polarized light. Okay, such kind of mixtures where you have optically active compounds present, but the optically active compounds are two enantiomers which have completely opposite angles or opposite direction towards which they divert the light with the same angle, and they are 50-50%, or you can say equimolar concentration is there due to the compensation, due to the cancellation of the shifting of the plane polarized light, or you can say because of the cancellation of opposite optical activity. When the plane polarized light come out of it, it shows like as if no optical activity has happened, and it shows there is no effect on the plane polarized, and hence no deviation. So such kind of mixtures are called as racemic mixtures. So let's very quickly go by the definition. What definition says? Definition says the racemic mixture is 50-50 mixture, as I mentioned, of two enantiomers because they are mirror images of each other and rotate the plane polarized in equal but opposite direction. And the solution is optically inactive. Why it is inactive? Due to external compensation, because one moves the light towards left and one moves the light towards right in the same angles, and hence the movement gets cancelled, or you can say hence the deviations gets cancelled. If the enantiomers are separated, the mixture is said to be resolved. If I have such mixture and then by using some method I separate the enantiomers out, I have a mixture in which R and S both the things are present, or both the enantiomers are present, and I use certain method to separate them out. In that case, the mixture is called as resolved. So now when we resolve it, when we separate the enantiomers, we say the mixture is resolved. There are many methods how to resolve the mixture, and we will be doing it going forward. Okay, so what we have got, this is equimolar mixture of D or L isomer, or R or S isomer, whatever you want to call it. This is called as racemic mixture, and racemic mixture is optically inactive, not because it doesn't have optically active compounds present. It is because it has optically active enantiomers present in equal number of moles, and hence due to the external compensation, the optical activity get cancelled out, and hence it shows there is no optical activity. So you can see I have written an example over here. I have a lactic acid here and lactic acid here. I have taken 2 enantiomers of it. So if you see, these 2 enantiomers are mirror images of each other. If I want to write their RNS structure, it will be like this. So this is your anti-clockwise, and this is R. So this is gonna be S. This, let's say, this R lactic acid moves the light towards right, and S lactic acid moves the light towards left. So they will be moving the light right and left in the equal angles, but in the opposite direction, obviously. And hence, due to the cancellation of the optical activity, the overall result of the racemic mixture is no optical activity. Okay. So this is about your racemic mixture, D and L mixture, R and S mixture, anything you can call it. Next, we'll talk about the polarimeter. Polarimeter, a slight introduction I had given when I started optical isomerism. And at that time, I told you that the apparatus what we use to check the optical activity of the molecules or the carbon compounds, or you can say organic compounds, is the polarimeter, where how the whole setup is, we have a light source from where the light will come, and this light will be unpolarized light. So basically it will be moving in all the directions. Then you will have a polarizer. Polarizer, what we generally take is Nicol prism, which will have some slits in it and will let only one type of light, or you can say the light which is moving in one direction, it will let it pass, and rest of the lights will get reflected back, or you can say will be absorbed or whatsoever. But whatever the light will pass, that light will be moving in only one direction, and that is why we call it as a plane polarized light. So we have got the plane polarized light after passing through the polarizer. The most common polarizer what we talk about is the Nicol prism, hence I have mentioned here the Nicol prism. Then it will go, or it will pass through a tube which contains the organic molecules. Basically, the organic molecules or organic compound has been kept in this tube to see the optical activity of that organic compound, whether it can show the optical activity or not. So here the concentration will be in grams per liter for the organic compound. The length will be L and will be represented by decimeter. Okay, now when I'll pass the light through it, we can see when the light will come out, whether there is a rotation or there is no rotation. If there is a rotation, then what is the rotation, in which angle it is the rotation, is it left or is it right, and what is the angle of the rotation, all that what we have to check. So how do we check it? There is an eyepiece over here, analyzer you can call it, okay, where again there is a slit, and slit is straight. Okay, so it's like I have an eyepiece over here with the slit in the center. Now when the light is passing through the organic compound, and if the plane polarized light is coming straight, then I can see the light through the slit. Let's assume this is the slit. I can see the light through that slit. Just in case if the light has moved to left or right, then in that case it is a movable eyepiece. Okay, so I will move and see where can I see the light, whether I can see the light at right or I can see the light at left. And according to the movement of the eyepiece, you can actually see the angles would be mentioned on that eyepiece itself. So it will show if it is moving towards right, then plus how many degree of angle rotation has happened, and if the light is visible towards the left, then minus how many angles it has been rotated. Okay, so that is checked by this movable analyzer, which is also called as eyepiece. So this is your whole setup for polarimeter. Mind one thing, that when we are talking about the organic compound, every single molecule of your organic compound participate in the optical activity and hence contribute in the optical activity if your compound is optically active. So definitely if the concentration varies, when you talk about the rotation angle of the light will also vary. That means if you have lesser concentration, in that case the rotation of the light will be relatively lesser. What we say is is optical rotation. And if the concentration of the solution is more, in that case what will happen? The rotation will be more. Now let's say if I give you 2 samples, and if the concentration is usually varying, but the solutions are of the same thing, Okay, let's say there is a compound A and this compound A has been dissolved in compound B. So basically I have made a solution of A and B and that solution is optically active, but the concentration is different. If you'll see it through the polarimeter, what will happen? If you'll see that optical activity through the polarimeter, because of the difference of concentration, you will find there will be a difference in the optical angle through which they have rotated the plane polarized light. So it is very, very difficult if I just go by this rule and if I just see the optical angle without standardizing the system, then every time when we are using a solution, you may find a different angle and you cannot fix it for a particular compound at a particular condition. Right. So basically, if in a laboratory there are 50 people who are working on the same compound, they all will get different rotation unless their concentration is exactly same. So here, to fix up this problem, what we had done, so we have introduced a new term which is called as specific rotation. And what exactly is the specific rotation? Specific rotation is the more standardized term which is constant for any compound at a particular wavelength and temperature. Okay, specific rotation is the value of rotation at a fixed wavelength and fixed temperature, and this value, specific rotation value, is not gonna change though the ratio of length and concentration will vary all the time, or you can say the values of length and concentration can vary, but in the result whatever the specific concentration will come out, that will remain fixed. So the values will change, but the ratio will always be fixed. So let's see what is specific rotation exactly and understand it in much more detail, because whenever we will be talking about the rotation, we will be talking about the specific rotation. We will not be talking about the actual rotation. Specific rotation is the more standardized term which has been designed in such a way so that we can fix up the value of rotation irrespective of concentration, irrespective of length of the tube for a particular compound at particular temperature and particular wavelength. Okay, so let's talk about specific rotation. It is a property of the chiral compounds and it is fixed at a particular temperature and particular wavelength and concentration. Okay, so if I have to represent it, how I'm gonna represent it? It is represented by alpha, where lambda nt tells that it is fixed value for a particular wavelength and particular temperature. So basically we are calculating the alpha at a fixed wavelength and fixed temperature. It's not gonna change. Now theta is the observed angle, which I said is it keeps varying when the concentration varies. This is the actual optical rotation angle which you see through your eyepiece, and it varies with the concentration. L is the length of your tube and C is the concentration of your compound. So when you talk about C is grams per milliliter, and if you talk about length is generally in decimeter. Theta is the observed rotation. Okay, and here what we do is when we are talking about this, so basically we are using our theta also, which was varying, length and concentration also, which could also vary and could change the optical rotation, and using all these three parameters, I have calculated a standard value for a compound for its rotation at a particular wavelength, particular temperature. Okay, now this specific rotation is very, very important when we talk about a compound, because this is what something we talk about, that for so and so compound this is the specific rotation, and because this value remains fixed, it becomes easier for us to do the further calculations. We use the observed rotation also when we have to find out the things called as enantiomeric excess. When you have a mixture of the compound where you have some R enantiomer also, S enantiomer also, and then you have to find out which enantiomer is greater, what is the purity of the compound, and so things. At that time we will be using both of these terms and calculating the enantiomeric excess, basically which enantiomer is in excess in a particular solution. So we will be using at that time this observed rotation also. Okay, and we will be using this specific rotation also. We can calculate enantiomeric excess only and only if we know the specific rotation of a compound. What is the specific rotation, or of an enantiomer, what is the specific rotation, then only I can calculate the enantiomeric excess in a solution. Enantiomeric excess is nothing else but, let's say, when the two enantiomers have been mixed together and a solution is present or a mixture is present, now I have to find which enantiomer is in excess and what is the purity of the compound, or what is the percentage composition of a compound in terms of R and S. Then we use these terminologies. Okay, so this is about your specific rotation, and this formula is very, 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 very important. So you have to remember this formula. You will be using it at various places, either directly to calculate the specific rotation, or when you have to derive the specific rotation for specific when you have to derive the specific rotation for the calculation of enantiomeric excess. What exactly is enantiomeric excess? We are just going to it, and we will understand exactly what it is, how do we calculate it, and what is the method of solving a question. So now let's understand what is enantiomeric excess. As the name suggests, you have taken a mixture, and in that mixture there is one enantiomer which is more and one enantiomer which is less. So it is basically a mixture where two enantiomers are mixed. Now both can be equimolar also, and there can be difference in the proportion also. Okay, and that proportion difference is basically called as enantiomeric excess. So see, what is enantiomeric excess? It is the measurement of the purity used for the chiral substances. So we basically check how pure your chiral substance is. Or when I talk about, let's say, a compound A, and I'm specifically looking for R or S configured enantiomer, but what I get is the mixture of it, there we check out for the purity, that how much percentage of R is there and what is the purity of the substance. It reflects the degree to which a sample contains one enantiomer in the greater amounts. Definitely, if I have, let's say, okay, we will discuss it in the example. So if I have one enantiomer more than the other, so definitely the moment of light will be according to the enantiomer which is more. Right? So if I have a plus enantiomer more than minus, so automatically my light rotation will happen according to the plus isomer. So a racemic mixture has enantiomeric excess of 0% because both are equal. In your racemic mixture, 50% is your R and 50% is your S. So when you ask how much is the enantiomeric excess over there, it's just 0%. When you talk about only one single completely pure enantiomer is present. Let's say if I say I have a solution of only R enantiomer or only S enantiomer. In that case, what will be enantiomeric excess percentage? 100%. 100% only one type of enantiomer is present. Whereas if I have a sample of 70% of one enantiomer and 30% of another, then what will be the enantiomeric excess? That means a particular enantiomer will be excess in how much quantities? 40%. 70% is one, 30% is another. Now 30% will get cancelled out. So 40% of a particular enantiomer will be in excess. So we can see this in table also. I have also tried showing you in the table. So let's say if I have 100% of plus isomer, then the specific rotation, how it's going to affect the specific rotation, let's talk about it. I have no minus enantiomer. So specific rotation is, let's say, alpha degree. If I have 100% of my negative enantiomer, then what will be the specific rotation? It will be minus alpha degree, right? So basically, depending upon what enantiomer is present, your alpha will also vary. Specific rotation is fixed for a compound, but definitely it is different for the enantiomers, right? It's like one has a plus alpha and another has a minus alpha, and if you take a mixture of it, it is going to change the specific rotation. If I have both 50-50%, then will the compound be optically active? No, I mean, it will not be able to rotate at all. So specific rotation will come out to be 0. If I have plus enantiomer as 75% and the negative isomer as 25%, then what is the excess enantiomer over there? So basically 25% of plus will nullify the 25% of your minus. So 50% of plus isomer will be left over, and only that enantiomer will show the optical activity. So optical activity will be 50% of alpha, that is alpha by 2. So alpha by 2 degree, alpha by 2 degree will be the specific rotation for this compound. So basically enantiomeric excess changes the observed rotation also. Specific rotation is the standard value, but observed specific rotation will change. Okay, observed specific rotation will change depending upon how much enantiomeric excess of which enantiomer is present. Specific rotation is a fixed value, just mind it. I'm talking about the specific rotation. The standard specific rotation is a fixed value. What is changing over here is the observed specific rotation. Okay, so we can calculate observed specific rotation only if you know the standard specific rotation. Now see, how do we calculate it? So percentage enantiomeric excess is what? Is basically the difference between two enantiomers which are present. How much is the difference divided by total quantity into 100. That is how exactly we calculate the enantiomeric excess. I told you if I have 75% of plus and 25% of minus divided by 100 into 100. So this is your 50% of enantiomeric excess. That's how we calculated it. So this is exactly is the formula. So you have, let's say, D and L enantiomer. So D minus L mode. Mode has been written over there so that you get the values always in positive, divided by total quantity present in the solution into 100. So this gives you percentage enantiomeric excess, which is also called as optical purity, because it tells you about the purity of a particular enantiomer in a compound. Now we can calculate this optical purity through a different formula also, and that is observed specific rotation by pure specific rotation. Pure specific rotation is nothing else but the standard specific rotation value which has been derived for a particular compound at particular concentration, lambda and temperature, right? Now this observed specific rotation will vary depending upon how much quantity of a particular enantiomer is present in a mixture. So both of these things are same. Percentage enantiomeric excess and optical purity are exactly same, and even this formula and this formula are exactly related to each other. Okay, so now let's see how we are gonna use this concept for a question. Questions are very simple, and you get such kind of questions in exam. If you have a mixture of 6 grams of plus butane 2-ol and 4 grams of minus butane 2-ol. So basically you have, we have not spoken about the percentage over here, we have spoken about the mass, and D minus L here you can have mass also, you can have volume also, you can have other concentration also, it can be anything over here. So you can just place the direct values. Okay. Is taken for a experiment, polarimeter experiment. The specific rotation, exact pure specific rotation for plus isomer is plus 13.5. This is the standard value. Okay, what all we have to find out? We have to find out percentage enantiomeric excess, optical purity, total percentage of plus isomer, total percentage of minus isomer, and observed specific rotation. Observed specific rotation means change. What change do you see? I mean the actual specific, or you can say the pure specific rotation has been already given, but due to this mixture, what change has happened in the specific rotation, that can be called as observed specific rotation. So first of all, let's find out the enantiomeric excess percentage. We can directly use this formula and solve it. So we are using D minus L, D plus L into 100. Now D minus L, that means 6 minus 4 will give you 2 divided by 10. So basically 20% of a particular isomer is in excess. Which isomer? Plus isomer. It is clearly visible that 6 grams is for plus and 4 grams is for minus. So 20% of plus isomer is in excess. That is what we have got for percentage enantiomeric excess. Now let's see how to calculate the other quantities. So next is, so we know that 20% of plus isomer is in excess. So basically, rest of the 80% is gonna be what? It is gonna be racemic mixture, right? So rest 80% is racemic mixture. So now if I have to calculate the total percentage of plus isomer and total percentage of minus isomer, 40% of plus is in racemic mixture and 20% is in excess. So basically total is 60%. 60% of your plus isomer is present in the whole solution. I mean, I don't think you have to use this method. You can just look at the compound and the values given and you can directly calculate it, right? 60% is the value of plus isomer and the 40% in total solution is 40% of the minus isomer. We have to calculate the optical purity. For optical purity, I told you optical purity and enantiomeric excess is exactly same thing. So unless I know 2 values out of 3 for the given formula, I cannot calculate the observed specific rotation. So that's the reason why we have calculated the enantiomeric excess earlier. So enantiomeric excess was 20%, so optical purity is also 20%, and pure specific rotation has been given for plus isomer, and plus isomer is in excess over here, right? So what is the value given for it? The value given for it was 13.7 degrees for a plus isomer. Right? So now I just have to calculate the observed specific rotation. You just multiply, divide, do all the calculations and it will come out as plus 2.7 degrees. So actual specific rotation for plus isomer is 13.7 degrees, but when you observe it due to this mixture and everything, because these two enantiomers have been mixed together, now if you see this organic compound in the polarimeter, rather than getting 13.7 degree as a rotation, you will see plus 2.7 degrees as the rotation. So there is a change in rotation due to this mixtures what have been got. You have not got the pure compound, you have got an impure compound where some sort of S was was also present, or some sort of negative enantiomer was also present. It was cancelling out, or due to the external compensation, most of the optical activity has been cancelled out, and only 20% part of the solution is showing the optical activity, and that is why the specific rotation has got decreased, and it is plus 2.7 degrees only. So this is how you have to calculate. Exactly this way you will get the questions on specific rotation or purity, optical purity, or enantiomeric excess, or finding out the percentage of one particular type of isomer. These kind of questions are very common. Go through it. I don't think there is much complexity in these type of questions. They'll be straight, simple questions. The only thing is you should know how to use the formula. So here we are done with the enantiomeric excess also. Let's see what's next we have. So let's start with the optical resolution and first understand what exactly it is. So we have understood what is enantiomeric excess and what is racemic mixture. So if I have a racemic mixture, I will have two different enantiomers over there, R and S. And just in case if we need to separate them out, the methodology what we use to separate them is called as optical resolution. So what exactly is the pattern we follow over there? See, when we talk about enantiomers, we clearly know that the enantiomers don't have different physical properties. They have exactly same physical properties, same boiling point, same melting point, and basically their all physical appearances are same. So you cannot use any physical method to separate them out. So the only method which is left to separate them out is the chemical method. So what exactly we do? We take a racemic mixture. We take a racemic mixture, we react it with any other compound which is optically pure compound. What do we mean by optically pure compound? That means it should be either R or S purely. It should not have any kind of mixture. Okay, so let's say I have a racemic mixture of A plus B. It is reacting with, let's say, C, which is optically pure compound. Now, when these two things will react together, two products will be formed. One is product of A with C. Let's say I have written AC, and the other product is B with C, which I have written as BC. Now, two products have been formed. C was optically active. Individually, A and B were optically active, but in the solution, it was a racemic mixture and the solution was optically inactive. So when A will react with C, it will form one kind of compound, and when B will react with C, it will form another kind of compound. And these two compounds will be optically active or not active, that we cannot say, but at least we can say that these two will be diastereomers of each other. Diastereomers. Okay, so separating enantiomers was very difficult because we could not use any physical method. But now, after the reaction, what we have got in the product is two diastereomers. And diastereomers do differ in their properties, in their physical properties, and you can separate them through various methods like distillation you can use, or crystallization you can use. There are a lot of other physical methods which you can use and separate them out. So you will separate these diastereomers from each other through any physical method, and once the separation is complete, now you can reverse the reaction. You have to choose a reaction in such a way that the above reaction which you have done over here should be reversible. So I'll do a reverse reaction to get A and C separated. Similarly, B and C separated. Okay, now what is there in this mixture? I have A and C, B and C. So at least A and B, which were enantiomers, are separated. Now I can use again the distillation or other physical methods to separate A and C out of it and B and C from each other. So this whole process is called as optical resolution. Why do we have to follow such a long process? Because separating enantiomers initially it's not possible because they do not get separated through any physical method. So we have to basically convert them into some form so that they can be separated through physical methods, and that's what exactly we do when we react it with any optically pure compound. In the product, we get diastereomers. Those diastereomers are separable. We separate them out and then we do a reverse reaction to get the original reagents back. Okay, this whole process is called as optical resolution. So exactly same thing, I have written it in the notes over here. We will just quickly go through the notes and see what has been written. Separation of the racemates into their component enantiomers is called as resolution. I told you in the racemic mixture we have to separate it out, is called as resolution. Why we cannot do it? Because why we cannot do it so easily? Because the physical properties are same. So we have to convert these enantiomers into some sort of distereomers so that we can separate them out. How can we do it? We have to do the reaction of the racemic mixture with enantiomerically pure chiral reagent. This is important. So the reagent with which you are going to react should be one form only and should be optically pure. Okay, optically pure means either it should be 100% R or it should be 100% S. It will give you a mixture of diastereomers, and these can be separated through the physical methods. So what is the example for it? We will see it soon. We will see the different examples which are very common in organic, and you will see are very majorly used for separating the enantiomeric mixtures. First, I'll show you an illustration, which is a very, very layman illustration, which has nothing to do with the organic, but you'll get a basic idea what exactly happens. So what I have taken over here is I have taken two different type of bowls. One is right-handed bowl, another is left-handed bowl. Both are exactly same in appearance. Both are identical in size and weight, so it is very difficult to separate them out. So what we have taken to separate them out is a nut which has threads inside, and those threads are right-handed threads. So when you'll try to engage the bolt and nut with each other, only right-handed bolt and right-handed nut will engage very, very properly with each other, whereas the left-handed nut and a left-handed bolt and right-handed nut will not get engaged properly, and it will help you in separating them out. This is a very simple method to show you that how to separate out the two different enantiomers from a mix where you cannot see the difference. It's not easy to separate them out. This chiral reagent, you can say this nut is acting as a chiral reagent which has a specific properties, and it will engage properly with a particular type of enantiomer and will separate them out. So this is not exactly the same process, but yeah, similar to this is what we follow in the organic compounds also. Now let's see the actual processes what we follow to get the optical resolution. I have taken an example over here. I have taken a reaction which all of you are quite aware of, and I really doubt anybody is there who doesn't know this reaction. So that is a sterification reaction. I have taken the carboxylic acid, okay, and carboxylic acid is in the form of racemic mixture, let's say. Okay, and or forget about the racemic mixture right now. Let's first discuss the course of the reaction, and then we will see it with an example. So if I take carboxylic acid and react it with alcohol, what exactly happens? The esterification reaction takes place. All of us know about it, and this gives us an ester. Now in this ester, if I add water to it, it will form carboxylic acid and alcohol. I mean, it will give you back the carboxylic acid and alcohol, and this process is called as Ester Hydrolysis. So that means this reaction you will do, and then if you add water to it, it is a reversible reaction. So this reaction is a very, very useful and helpful reaction in separating out the racemic mixture of carboxylic acid or racemic mixture of alcohol, and then you use carboxylic acid. Either way, any compound it can be. So I have taken an example over here. What I have taken two different carboxylic acids and basically the enantiomeric mixture of it. So what is the enantiomeric mixture here? We have carbon with COH, CH3 phenyl group, and hydrogen R and S. These two in the equal proportion I have taken. So it is a racemic mixture. Now I want to separate them out. For separating them, what I'll be taking any alcohol which is optically pure and active. I have taken this alcohol over here, which is R dash. I have mentioned it as R dash so that we can differentiate between R of this and R of this. Okay, that's the reason I have written R dash. R dash is just to write the differentiation between the alcohols R and the carboxylic acids R. So I have taken an optically active alcohol over here. Now when I'll react this alcohol with this enantiomeric mix, first of all, R form of carboxylic acid will react with R dash form of alcohol and will form a respective ester. So it will lose OH from here, hydrogen from here, and this is how the molecule will be formed. All of you please look at it very, very carefully. Okay, so it will form this this compound which will be in the configuration of RR dash. Why RR dash? Because any reaction is not happening on the chiral carbon. This is my chiral carbon. Chiral carbon is not involved in case of reaction, and here also this chiral carbon is not involved. So there you can say special arrangement or their configuration is not gonna change unless chiral carbon is involved in the reaction. The configuration will not change. So the alcoholic part will still remain R dash and the carboxylic acid part will still remain R and the compound will become RR dash. Exactly same way, when this alcohol will react with S, what will happen? The compound formed will be SR dash. So basically RR dash, SR dash both are optically active but both are diastereomers of each other. So how can I separate these diastereomers? Through the fractional distillation by heating them up and then separating out at different boiling points and so on. So now this A compound and B compound can be easily separated through the fractional distillation. Now after fractional distillation, what I'll get? I'll get two esters. One is RR dash and another is R dash S. This is what I'm gonna get. So what we'll do next? So this is what exactly I have got. Now these esters have been separated properly. These were diastereomers, could be separated through the fractional distillation. And now I'll do hydrolysis. Won't I get back my R acid and R dash alcohol, S acid and R dash alcohol? Yes. Now in the mixture I will have separated acid and alcohol. Now again I can use some physical method to separate these acids and alcohols from each other and I will get my R acid separated and S acid separated. So this whole process is called as optical resolution. It is mandatory to use optically pure reagent to separate or to do the optical resolution. Now instead of alcohol we could have taken the pure amine also, because the reaction of RCOH with RNH2 is like this. I mean, OH will go from here, hydrogen will go from this, and it will form RCO. Let's write it as R dash, RCONH R dash. So basically I could have got an amide. And again you do acidification, acidified water you add to it, and what you'll again get carboxylic acid and the respective amide. So this reaction is also reversible reaction, which you have learned in carboxylic acid chapter already. So instead of alcohol you could have taken amine, but again amine should be it should be optically pure amine and it will give you the same set of reaction. The only difference will be in the product. You will be getting an amide, and then amide can be easily converted into the alcohol and its amine back. Now let's see a question very quickly. Let's say what kind of questions you can get from this part. Let's see if I have an enantiomeric mix of an acid, how it can be resolved. It can be resolved by the first compound given is the pure alcohol, second is given as a mixture of alcohol, third is given as pure amine, and fourth is given as a mixture of amine. This is a multi-answer correct question. So optically pure alcohol as well as optically pure amine will help in resolving the enantiomeric mixture. Okay, so this is about what is optical resolution. I think you are clear now. Enantiomeric mixture, what it is, racemic mixture, what it is, what is enantiomeric purity, and what is enantiomeric resolution or optical resolution. Everything we have discussed till now. Next I'm going to discuss is, if you remember when we started the session, at that time I told you that I will tell you why tertiary amine, even though it is chiral, if you have an sp3 amine or sp3 nitrogen, even though it is chiral, why it cannot show the optical activity. So we will just talk about the reason why it cannot show the optical activity just now. Okay, so now let's quickly talk about the reason for tertiary amines optical inactivity. When we talk about the tertiary amine, we have three different groups present here, R1, R2 and R3, and I have a lone pair over here, which makes this whole system as sp3 and chiral. But still we say that this whole system is optically inactive. Why? Reason is there is a special type of flipping which happens in the amines. Now what that flipping is, this sp3 hybridized nitrogen is pyramidal in shape. Why it is pyramidal in shape? And why it is pyramidal in shape? This pyramidal shape is because of the lone pair. So now this is sp3 pyramidal compound, and there is a sort of flipping which happens on this nitrogen, because of which the optical activity gets cancelled out. Now what is that flipping? What is this pyramidal inversion or flipping, which is also called as umbrella inversion? What exactly it is? Let's see. I have nitrogen and I have the lone pair here on the top, and I have three R groups like this, arranged like this. And now what happens is, no matter we are talking about tertiary amine or we are talking about the normal nitrogen with any group present on it, there is a movement of electron happens from top to bottom. So basically there is a p orbital over here, and these electrons keep moving from up to down, up to down, up to down. I told you this lone pair is not participating in the hybridization. So there is a p orbital here, and these p electrons goes from upper lobe to lower lobe, lower lobe to upper lobe. That's how they keep switching. Okay, and these three these three bonded groups are away from the lone pair because of the lone pair bond pair repulsion. Now when this lone pair will try to come down, when I have this p orbital and this lone pair tries to come down, what will happen? These three bonded groups will get repelled and will go up. Basically will try to avoid the repulsion, and hence will move from their positions and will go up. So this is like an umbrella inversion. You must have seen many a times when you are carrying an umbrella and it's too windy. The umbrella is like this. When it's too windy, it just becomes completely opposite. It just becomes like so. It's the U shape like this becomes the U shape like this. So it gets completely inverted. This is what exactly happens in nitrogen. When lone pair tries to come in the down lobe or the lower lobe, all the three bonds will go up. Okay, so it will be like this. There will be a transition state which will be forming where the electron will be moving from upper lobe to lower lobe. So I have just drawn a transition state over here which may form. I mean, we are not very sure whether this is forming or not, but we assume that it will be forming when this transition is happening, and it is highly unstable state where these are, it's like this. When you have one, let's say this is the nitrogen, the intersection is nitrogen, and these are the three groups. So when the electron pair will start coming down, this will flatten. So basically these three groups which are attached on the nitrogen will flatten, and it will become like this. So they will neither be up nor be down, they'll be flat, and the electrons are going from up and down. And then when the total movement of electron will happen, basically they'll come to the downer lobe. What will happen? These will get completely away from the electron, and these three bonds which were down here will go and shift up like this. So it is an inverted molecule. This is a highly unstable transition state. If it forms, I mean, theoretically we are forming it, but if practically it forms, it will not stay for a long time. You won't be able to even notice this kind of transition state forming. So I have this compound initially, and now the spatial arrangement has got changed and it has got flipped, right? When you look at the first compound and the second compound, okay, the compound has not changed. Basically just the arrangement has changed a bit. Aren't these mirror images of each other? This compound and this compound is mirror image of each other, right? Because they are mirror images of each other, now in the solution, or you can say the compound, is always in the form of racemic mixture. Why? Because one molecule will be converting into another will be converting into one. So 1 to 2, 2 to 1, 1 to 2, 2 to 1, that kind of transition will be happening all the time, and this transition is very rapid. Very rapid. So some molecules will be in the state 1, and some molecules will be in state 2, and some will be transitioning. So always your structure, your compound will have the movements going on inside. Flipping will be happening. It will be like this and 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 this. Right? And because of that, the mixture or you can say the compound is actually in the racemic mixture form, which looks like chiral. It's not chiral, it is a racemic mixture, and that is the reason why it doesn't show the optical activity. So first and two, as I mentioned, are the mirror images, and they form the racemic mixture, and due to the formation of the racemic mixture in the whole compound, they are not able to show the optical activity. As I mentioned, flipping is very, very fast, especially when you talk about ammonia. As I mentioned, it is not very specific to tertiary amine. It is specific to any, it is with any nitrogen compound, this thing will happen. Why we are talking about tertiary amine? Because tertiary amines are the groups where we can see the chirality. Okay, where these are chiral, whereas other amines, secondary, primary, ammonia, these are not chiral. So optical activity we can speak about only tertiary amines. We cannot talk about the other reagents. Okay, so in case of ammonia, if you talk about this flipping happens 4 into 10 raised to power 10 times in a second. I just missed writing in a second. So 4 into 10 raised to power 10 times in a second at a room temperature. So that's how the flipping is, and that's why you cannot see the intermediate state also. Now, example where there is no flipping. Is there any example where there can be no flipping, or we can say the compound is optically active? Yes, we have such compounds, and those are important compounds. So if your nitrogen is a tertiary amine is the part of a cyclic ring, then the cyclic ring cannot do the flipping due to the steric hindrance or because it's bulky and so on. Mind it, open chain structures are not bulky. Okay, so no matter how bulky your R group is, you won't say that can this reverse because this is a very bulky group. We are not talking about that. We are talking about only cyclic rings because cyclic rings get strained and they are not the ones which can rotate or flip very easily. Okay, so if your nitrogen is present on a cyclic ring, flipping is not possible, and that's the reason this nitrogen will show the chirality and your electron will remain static. It will remain fixed at its position. It will not go to the downer lobe. Okay, this is example where even though you have a tertiary amine, optical activity is still possible. Apart from that, there is one more usage of this concept, and let me just explain you that. So another thing is when you talk about nitrogens are good bases, right? I mean, we talk about the basicity, strength and all that. And here you can get a question like this. You have this compound, look at this nitrogen. This nitrogen is optically active. This nitrogen is a chiral nitrogen. And here also we have a chiral nitrogen. But what is the difference between this nitrogen and this nitrogen? We don't have to actually go by chirality here because we have nothing to do with the chiral carbons here. We can just simply talk about the base. We have to just see which one is the better base. Here, the concept of flipping will be used. Okay, though we are not talking about chirality at all. If I have to talk about a better base, what is the base? Base is the one which can accept the H plus thing or it can share its lone pair with something. So that is basicity. So availability of lone pair is the basicity or the basic strength. Now, when you're talking about the flipping, electron is jumping from one place to another, one place to another, one place to another. So what will happen if the flipping is happening? The electron will not be static or will not be localized. It will be always moving. An attack on those electrons is gonna be a little difficult. So when you compare a localized pair of electron and delocalized pair of electron, which is more reactive? The localized pair of electron is more reactive, or you can say more available, right? So here also the same concept we are going to use. I have this cyclic ring. I told you it cannot flip because of the cycles have angle strain and so many other things. So basically the rotation is not possible in the cyclic rings. So the cyclic rings, you just remember that they cannot flip, they cannot rotate, okay, because the strain happens, the angle strain happens, and then flipping of cyclic rings is not possible. So this lone pair will be static at its position, whereas if you talk about this lone pair will be flipping from up and down, up and down, up and down. So availability of lone pair is better here than this. So if they ask you such question, which of the two is the better base? Obviously the cyclic one is gonna be better base because there is no flipping and the electron pair is localized. Okay, so this is the another usage of this concept. There can be many other ways to find out the basic strength, but this is also one of those. Now let's talk about the last concept of your optical isomerism is alternate excess of symmetry. What is alternate excess of symmetry? We have already spoken about excess of symmetry. Now this is one more type of symmetry, that is alternate excess of symmetry. So what is alternate excess? Here if we talk about a cyclic ring, okay, any compound we can take. I have taken a rhombus shaped structure where we have two groups attached, chlorine, and this is in the trans form. Okay, now I have passed a line through the center. You can see I have passed a line through the center and I rotate the molecule by 180 degree. So what will I get? I will get this compound. Please look at it carefully. This chlorine which is down will come up and the chlorine which was up will come down. You rotate it like this. This is what exactly is going to happen, right? Now if I place a mirror on the perpendicular direction to this axis what I had taken initially, or if I place the mirror here like here in the perpendicular direction, what will happen? Again a mirror image will be formed. These two are not mirror images. This is just a rotation after 180 degree. I have got this. Now I place a mirror down here. What will I get? This chlorine will be here, this hydrogen will be here, this chlorine will be here, and this hydrogen will be here. Isn't this compound and this compound exactly same? Look, exactly, try comparing. It's exactly same molecule, right? So when I rotate a particular compound at a certain angle, that angle should be 360 by n. Okay, if I rotate it through a certain angle and then after rotation I place a mirror down there or on the or in the perpendicular direction, and if I get exactly same reflection as the original molecule, then that axis on which I had rotated the molecule is the axis of symmetry, alternate axis of symmetry. And here I have rotated it to 180 degree, hence my n is gonna be 2, and I can call it as S2 symmetry. Understand it again with another example. I have taken a trans molecule or trans alkene over here. Now let's suppose 180 degree is not a fixed angle. I am just giving you that I am rotating the molecule to a 180 degree. Rotation you can do to 90 degree, 180 degree, and in the multiple proportion of this 360 by n. Okay, so if I rotate it to 180 degree, what will I get is methyl, this methyl will come down here, this methyl will come up here, and hydrogen at these positions. Now if I place a mirror down here, what will I get? I will get this methyl here, and hydrogen here. Just compare the first molecule and the third molecule. Isn't the first and third is exactly same? It's identical. So basically on rotation at 180 degree and then placing the mirror in the perpendicular direction gives me the exactly same molecule, and hence this second molecule, the second compound contains S2 symmetry. Why S2? Because I have rotated it to 180 degree and then n comes 2, so I call it as S2 symmetry. This exactly is the axis of symmetry. Not axis of symmetry, alternate axis of symmetry. So how can we define it? We can define it as alternate axis of symmetry is nothing else but it is a line along which if the molecule is rotated by 360 by n degree and the image is observed in the perpendicular plane, then it should give you exactly same reflection as the original molecule. If you get that after rotation on that axis, then that axis is called as alternate axis of symmetry. Here there is one important saying about this alternate axis of symmetry. In any compound, we know that if POS and COS is not present, then the compound is optically active. Sometimes they also speak in the terms of alternate axis of symmetry, and if in any compound alternate axis of symmetry is present, then there is definite thing that the COS will also be present. COS is very much related to alternate axis of symmetry. COS will be present and hence your compound will be optically inactive. We can also say that if AAOS is present, then the compound is gonna be optically inactive. If they ask you such question, they don't give you POS and COS and they just talk about the alternate axis of symmetry. If it is present, then it is completely optically inactive because COS would be present, and the condition for a compound to be optically active is that POS and COS must not be present. Now look at another compound I have taken over here. I have taken this compound. Assume, again I have taken a cyclic structure and I have 4 groups attached to it. 4 exactly same groups. Only thing is their configuration is different. Assume one group present here is R group, R configured group, then S here, and R here. So these, it can be any chain with R configuration and S configuration. The chains are same, only the configuration is varying. Then what will happen? This is a very important question, by the way. These kind of questions are quite important. I have not written the whole structure because it would have made the whole molecule look very clumsy and I don't want to do it. So you assume any structure which is R configured and S configured and has been placed in these positions. Now if I'll rotate this molecule to 90 degree, just it's like this is rotated like this, that's all. So what will happen? If I'll rotate it to 90 degree, this R will come here, this S will come here, this R will come here, and this S will go there. That's how exactly it will look like, right? Now I'll place a mirror down here, and what will I see? Always remember one important thing, that R is the mirror image of S and S is the mirror image of R. Mirror image of R is not R, mirror image of S is not S. Okay, so when I'll place the mirror, what will I see? This R will be here as S and this R will be here as S. I think I have written it wrong over here. It should have been here. My bad. I think I have done typo here. Okay, I have done a big typo over here. I'll just redraw it. So it will be something like this. So here I'll get S over here and S over here. And for these S, If the reflection I'll see, it will be R over here and R over here. Isn't this exactly same as the original molecule? It is exactly same, right? What is the symmetry over here? 360 divided by 90 comes out to be 4. So n is 4. So Sn is generally the symmetry element and we represent it through this way. So we have S4 symmetry in this molecule. So this AAOS is important not to calculate the symmetry but to see if a compound has been given with AAOS. And they mentioned this compound as AAOS. Now tell whether this compound is optically active or not. What will you clearly say? No, it's optically inactive. Why? Because it must have a COS present in it. Okay. So here we are done with optical isomerism, all different type of concepts which were required in it. Next we'll be talking about conformational isomers in the next class. Now you can try solving all type of questions from your module, try it out and let's discuss it in the doubt session.